Hello everyone, thanks for watching this video. Today I'm going to talk about our work, Group GCM, which is a GCM-based model for 3D human pose estimation. 3D human pose estimation aims to regress the 3D positions of body joints in the camera coordinate system from images or videos. It plays an essential role in numerous applications such as action recognition, computer animation, and human-computer interaction. But because of estimating from the monocular observations, there are many challenges. The main problem is depth ambiguity. Both 2D and 3D pose can be naturally represented by a skeleton graph in the form of 2D or 3D joint coordinates, so that graph convolutional networks have been applied for 3D HOPE recently. GCM-based approaches not only learn a compact representation defined on graph nodes, but also explicitly capture their structural relationships. Their superior performance over the fully connected networks proves that relational reasoning is critical to mitigate the depth ambiguity. Spatial aggregation is the key component of GCM. Many methods have been proposed to increase the feature aggregation capability of GCM. GEL proposes a semantic GCM by multiplying a learnable mask to the skeleton-based affinity matrix to capture semantic information such as local and global node relationships. Zoe proposes modulated GCM. They use weight modulation to resolve the limitation caused by a shared feature transformation for different nodes while retaining a small size. However, these approaches share a spatial aggregation kernel for all channels, which is called coupling GCM. It is not an optimal choice since different channels represent different types of motion features and relationships between joints are not always the same, which limits the flexibility of feature extraction. In contrast, every channel has an independent spatial aggregation kernel in CNNs, capturing different spatial information in different orientations, color, and frequencies. Why not try to use channel-wide spatial aggregation kernels in GCNs? It is because that if we set channel-wide spatial aggregation kernels in GCNs, it makes the model too heavy and increases the difficulty of optimization. To resolve this issue, we introduce group convolution to GCNs similar to the group convolution in CNNs. We also divide the channels into G groups. Every group has an independent adjacent matrix in group GCM. Channels in a group share one adjacent matrix to reduce the redundancy of the adjacent matrices. Following this idea, we remain two challenges. Firstly, how to choose appropriate adjacent matrices for these groups. Secondly, the channel groups are independent of each other. As a result, the set of independent group convolution may not be globally coherent, leading to poor performance. How to realize information interaction between different groups. We consider four different adjacent matrices to learn the relationship beyond the natural connections of body joints. Symmetric matrix, which encodes the human skeleton symmetrical structure for joints that have a symmetrical counterpart, such as leg joints. High-order matrix, which explicitly encodes first-order and second-order kinematic connections for joints, such as shoulder-elbow, shoulder-wrist. Self-learning matrix, which can create new connections and existence and strength of connections are updated during the training process. Self-adaptive matrix, which expresses a data-dependent matrix to determine whether a connection exists between nodes and how strong the connection is. Given two node features, we use two embedding functions to reduce feature dimension before sending input features into correlation model function. To overcome the side effects brought by group convolutions, we introduce group interaction to account for the information of different groups. In addition, we consider 4 group interaction methods. For adding interaction, the results of individual convolution of each group are added together to realize the interaction of information between different groups. For connecting interaction, first, we concatenate the channels of each group. Then we copy it g times for group convolution to generalize the features of each group independently. For shuffling interaction, this structure is similar to that used in ShuffleNet, which splits the channels in each group into G subgroups and feed each group with different subgroups. For example, suppose a group GCN layer with G group whose input shape is G, D. We first transpose it into D, G, flattening and then reshape it back as the input shape. The channel shuffle operation is efficient and elegant. For interleaving interaction, we introduce interleaved group convolutions proposed by IGCNet into GCN. It can be simple and efficiently implemented by a channel permute operation which permutes input shape of the group GCN layer from G, D to D. G, the number of channels group and the channels of each group are interchanged. That means the channels in each group of output come from different groups of input. We use the network architecture for 3D hope and compare different decoupling aggregation approaches in our experiments. We use 2 group graph convolutional layers as a building block with residual connections. Each group graph convolutional layer is followed by a batch normalization and a RealU activation function except for the last one. We compare the different group interaction methods. By default, decoupling graph convolution degenerates into coupling graph convolution, which serves as baseline in our experiments. We fix the spatial aggregation kernel of each group to be self-learning matrix for fair comparison. We can draw the following conclusions. Firstly, compared to coupling graph convolution network, group graph convolution network achieves higher performance. It is found that both adding interaction and connecting interaction are superior to shuffling interaction and interleaving interaction. Adding interaction and connecting interaction improve upon baseline by a large margin while only increase few parameters. However, shuffling interaction and interleaving interaction performs worse than baseline. Adding interaction and connecting interaction are used as our default setting in the following discussion. Secondly, the number of groups has a significant impact on the performance of 3D hope. We do not need to decouple the adjacent matrix of every channel. It is shown that the performance first improves with more groups. However, with more than 8 groups, the performance drops. 4 8 groups are enough for 3D hope. Then we study the impact of different spatial aggregation kernels on the 3D hope performance. We fix the number of groups to be 4. We fix channels of each group graph convolutional layer to be qubitics. The result is shown in Table 5 and Table 11. Self-learning matrix plays an important role in the performance of the group GCN because it allows the graph to include extra edges beyond the predefined. However, self-adaptive matrix performs worse than self-learning matrix indicates that too much freedom can lead to overfitting and harm the generalization ability of group GCN. Symmetric, high-order and self-adaptive matrices have little effect on the performance of models. Compared with other baselines, our methods achieve the state-of-the-art performance with either QD detected or QD ground truth as input. Note that our methods only have around 1/4 parameters of the second-place method. Then, we compare the group GCN with some state-of-the-art methods on CDHP dataset. Group GCN outperforms others on CDHP, indicating that our approach has strong generalization capabilities to unseen datasets. At last, let's watch the qualitative results of Group GCM. Thank you for watching.